Dear students, welcome to the last part of heat treatment of steels. In this video, I will discuss the heat treatment processes, tempering, mud tempering and ostempering, and time, temperature and transformation diagram. Tempering is a heat treatment process where the steel is reheated after the hardening to a temperature below lower critical point for both hypo and hyper-eutectoid steel. Then the steel is held at this temperature for sufficient period of time, which is about 4 to 5 minutes for each millimeter thickness of the metal, and finally cooling the heated steel in the air. The different tempering processes are low temperature tempering, medium temperature tempering, and high temperature tempering. In low temperature tempering, the steel is reheated at a temperature range varies from 150 degrees centigrade to 250 degrees centigrade. And after this treatment, the internal stresses are reduced and the ductility is increased, but the extra hardness is not removed. During the medium temperature tempering, the steel is heated at a temperature range from 350 degrees centigrade to 450 degrees centigrade, and after this treatment the extra hardness of the steel is reduced to some extent. During the high temperature tempering, the steel is reheated to a temperature range of 500 to 650 degrees centigrade, and after this treatment the extra hardness in the steel is completely removed. The advantages of tempering processes are extra hardness and brittleness of the hardened steel is removed. Residual stresses set up in the steel is released. The ductility and the toughness of the steel is improved. Percentage of elongation of the steel is increased. The limitations of these processes are it is only applied to restore the ductility of the material. In case of increasing the hardness of the steel, this process is not suitable. Holding time for the job is one of the important factors in this operation. The range of temperature should be maintained properly by this process. The applications of different tempering processes are low temperature tempering is applied to cutting tools for carbon steel and low alloy steel. Medium temperature tempering is applied for coil spring, laminated spring, hammers and chisels, etc. And high temperature tempering is applied for connecting rod, shaft and gears, etc. Generally, the most useful type of uninterrupted quenching is mud tempering. In this process, the steel is heated above the critical range to make it all austenite. Then it is quenched into a salt bath, maintaining a temperature above the temperature at which martensite formation starts. The temperature range is in between 150 degrees centigrade to 300 degrees centigrade. Then the component is soaked in the bath until its temperature comes down to the bath temperature. But it is not allowed to be immersed for a longer period. And lastly, the austenite starts to decompose. Then it is removed from the bath and cooled further to room temperature in air or oil. During the second part of cooling in air or oil, the austenite is transformed into martensite. The advantages of mud tempering are: the chances of setting up of residual stresses are minimized and hence of usual quenching cracks. Since less amount of austenite is retained in the steel structure, so the changes in volume are minimal. Because of the simultaneous and uniform transformation occurs throughout the metal, the chances of warping are very less. The limitations of this process are: since it is a misnomer, it is not a tempering process but a hardening process. The main limitations of this process are that in two different steps of cooling, the process leads to the final structure of martensite with retained austenite in the steel. Thus, it enables the formation of martensite without the formation of bainite. This process is employed for producing martensite during the manufacturing of the components such as toolbox, sprockets, J-hooks, ring gears, wheel hubs, suspension brackets, differential housing, conveyor links, tool holders, etc. Austempering is the process in which the steel is heated above the critical range to make it all austenite. Then it is quenched at a critical cooling rate into a salt bath or lead bath held in the bainite range between 205 degrees centigrade and 425 degrees centigrade. Then the steel piece remains in the bath until the austenite is completely transformed into bainite, and then it is allowed to cool to room temperature. Tempering operation is rarely needed after austempering operation. The advantages of austempering are: greater ductility and toughness along with high hardness is produced. There is a less chance of distortion. Less danger of quenching cracks because the quench is not very drastic. The limitations are: the size is restricted to relatively thin sections so that the entire piece can be quickly attain the temperature of the quenching bath. For steels of high hardenability, the larger sections can be used. The process is very lengthy. Long time required for isothermal transformation of austenite to bainite. The austempering operation is applied for power blades, clips and clamps, cutter and mixture blades, transmission gears, wear plates, etc. TTT curve time temperature transformation curve or S curve or isothermal curve. This diagram is the plot between temperature and time, showing how the transformation takes place at constant temperature for a carbon steel as the austenite is cooled. In the diagram, curves C1 and C2 represent the beginning and ending of the transformation from austenite to different structures, depending on the temperature at which the transformation takes place. When the austenite is suddenly cooled to 575 degrees centigrade and kept at this temperature in the diagram curve ABCD, then the transformation from austenite to pearlite starts at C and completes at D in the diagram. In the diagram above 600 degrees centigrade, it is seen that the transformation period goes on decreasing and coarse pearlite forms due to the less time for the formation of new nuclei. Below 600 degrees centigrade in the diagram, the transformation time is more and fine pearlite is produced. Such a transformation taking place at constant temperature and is known as isothermal transformation. In the diagram, for the curve ABEFG, austenite transforms into bainite, and it is seen that around 220 degrees centigrade, curve CFC1 in the diagram is flat, and the cooling below 220 degrees centigrade results in instantaneous transformation of austenite into martensite. The heat treatment of steel is now completed. Thank you students for listening the lecture.